Obesity is usually discussed in the context of diabetes, cardiovascular disease, and cancer. In this video, we're going to look at a large Lancet multicohort study examining the association between adult obesity and the risk of severe infections, including hospitalisation and death, across a wide range of pathogens. Rather than just summarising the results, we'll focus on how to read the paper, the study design, baseline characteristics, and how to interpret the findings carefully as clinicians and researchers. Okay, so as usual, after a brief figure-by-figure overview, we'll move into paper craft. If you're watching this more for research methods or exam prep, feel free to skip straight to that section. But firstly, let's start with the baseline table. This sets up the scale and comparability of the cohorts. We're looking at around 68,000 participants from Finland and almost 500,000 from UK Biobank. The UK Biobank cohort is older on average and has higher prevalence of overweight and obesity, which becomes important later when we think about absolute risk. Crucially, severe infections were excluded at baseline, so this is truly prospective risk. Figure 1 is the backbone of the paper. It shows a clear, stepwise dose-response relationship between BMI category and severe infection risk. As BMI increases, so does the risk for hospitalisation, death, and the combined endpoint. Class 3 obesity stands out, with roughly a threefold higher risk compared to healthy weight, and this pattern replicates almost perfectly in the UK Biobank cohort. Figure 2 asks the obvious question: is this just confounding? The answer is no. Even after adjusting for demographics, smoking, alcohol, physical activity, cardiometabolic disease, and more, obesity remains independently associated with infection risk. The effect size shrinks slightly, as expected, but it absolutely does not disappear. Figure 3 stress tests the findings across subgroups. Younger, healthier individuals, the association holds. Older individuals, smokers, people with chronic disease, still there, though slightly attenuated. The consistency here is striking and argues against this being driven by one vulnerable subgroup. Figure 4 is where the paper really distinguishes itself. Obesity isn't linked to just one type of infection, it's associated with bacterial, viral, parasitic, and fungal infections, both acute and chronic. The strongest signals appear for viral infections and skin and soft tissue infections, while HIV and tuberculosis notably show no association, likely reflecting reverse causality. Figure 5 scales everything up to the global level. By combining their risk estimates with global burden of disease data, the authors estimate that around 1 in 10 infection-related deaths worldwide may be attributable to obesity. This fraction spikes during the COVID-19 pandemic and varies dramatically by region, tracking obesity prevalence. Taken together, the figures tell a remarkably coherent story. Obesity is not just a metabolic disease. It's a major, independent, and globally relevant risk factor for severe infection. Before we get properly into papercraft, it's worth pausing briefly on study design, because this determines what kind of conclusions we're allowed to draw. So this is a prospective observational multi-cohort study. Body mass index is measured at baseline, participants are then followed forward in time, and the outcome is the first severe infection, defined as either a hospital-treated infection or an infection-related death. Importantly, anyone with a prior severe infection is excluded at baseline. That establishes the correct temporal order: exposure first, outcome later. The authors then repeat the same analysis in an entirely independent cohort, the UK Biobank, which serves as a replication rather than a validation. The goal here is robustness, not model optimization. This design is very strong for identifying associations, for assessing dose-response relationships, and for testing consistency across populations. What it does not do is prove causality. There is no randomization, and residual confounding is always possible. So, when you read this paper, the correct interpretation is not obesity causes infections, but rather obesity is consistently associated with a higher risk of severe infection across populations and pathogen types. Keeping that distinction clear is essential, especially when translating findings like these into clinical or public health discussions. With that design in mind, let's rewind to the start of the paper and look carefully at who was actually studied. Most clinical and epidemiological papers include a baseline characteristics table, often Table 1, and its role is very specific. The table is descriptive. It tells you who was studied, how the exposure is distributed, and what clinical or demographic factors might influence the results later on. It's not designed to test hypotheses or demonstrate balance. Most clinical and epidemiological papers include a baseline characteristics table, often Table 1, and its role is very specific. The table is descriptive. It tells you who was studied, how the exposure is distributed, and what clinical or demographic factors might influence the results later on. It's not designed to test hypotheses or demonstrate balance. When you read a table like this, start by orienting yourself to the population. Look at the cohort size, age, and sex distribution. In this paper, the Finnish cohorts are younger, while the UK Biobank participants are older and have a higher prevalence of overweight and obesity, which helps explain differences in absolute risk and precision later in the figures. Next, look at how the exposure is defined. Here, BMI categories are clearly specified, including obesity class 1 through 3. This clarity is essential because everything that follows depends on these definitions. Then scan the clinical and lifestyle variables. Smoking, physical activity, cardiometabolic disease, diabetes, and socioeconomic status are all visible. This tells you, as a reader, where confounding might arise and why adjustment is needed in the statistical models. But importantly, this table does not include p-values or stratification by outcomes, and that is appropriate. In observational studies, baseline differences are expected, and outcomes occur after baseline, not before. If you're writing your first Table 1 for a thesis or a paper, focus on summary statistics. Use means and standard deviations for approximately normally distributed variables, medians and interquartile ranges for skewed data, and counts with percentages for categorical variables. The goal is clarity, not completeness. A good baseline table gives the reader the context they need to understand and appropriately question everything that follows. In summary, Table 1 provides context, not conclusions. Now, every good paper deserves a careful discussion of its limitations, not as a weakness, but as a guide to interpretation. The first and most important limitation here is study design. This is an observational study, not a randomized trial. That means the findings describe strong and consistent associations, but they cannot prove causality. Even with extensive adjustment, residual confounding is always possible. The second limitation relates to the exposure. Body mass index is practical and is widely used, but it's an imperfect proxy for adiposity. It does not fully capture fat distribution, metabolic health, or immune function, all of which may be directly related to infection risk. The authors partly address this by showing similar results using waist circumference and waist to height ratio, which some researchers do consider preferable in this context, but some biological nuance is inevitably lost when you use any of these measures. Using all of them is a pretty good move, though. Third, the outcomes are restricted to severe infections captured through hospitalisation and mortality registries. This is a strength for specificity, but it means milder infections managed in the community are not included. The results therefore speak to severity and prognosis, not overall infection incidence. Finally, although the cohorts are very large, they are not strictly population representative. Finnish public sector workers and UK Biobank participants differ from the general population in health and socioeconomic characteristics for their respective countries. This affects estimates of absolute risk, although relative associations do tend to be more robust. Taken together, these limitations don't undermine the findings, but they do define the boundaries within which the results should be interpreted, discussed, and applied. Understanding limitations when you're reading a paper isn't about finding faults, it's about knowing how far the data can reasonably take you. To close, it's worth stepping back and synthesizing what this paper really contributes and how it's being received. Methodologically, this is a strong observational study. Across two large cohorts, increasing obesity severity is consistently associated with a higher risk of severe infection, including hospitalisation and death. The dose-response pattern and replication make this a robust association. At the same time, the limits are clear. This study does not prove causality, and it does not speak to mild community-managed infections. Its conclusions are about severity and outcomes, not infection risk in general. In terms of reception, the study has been widely covered in the medical press, including the BMJ and Eureka Alert and specialist clinical outlets. Coverage has generally been accurate in reporting the size and consistency of the association, particularly the estimate that around 1 in 10 infection-related deaths globally may be attributable to obesity. Although, of course, we do need to be careful about causality here because we are kind of tiptoeing towards an overstatement. Where interpretation can drift further is in headlines that imply direct causation or that frame obesity as a single modifiable lever for infection prevention. The authors themselves are more cautious, of course, emphasizing association, context, and the complexity of obesity as a risk factor. Expert commentary has also highlighted the need to avoid oversimplification, stigma, or unrealistic expectations around prevention and treatment. Taken together, the real contribution of this paper is not a new clinical rule, but a reframing. Obesity should be considered alongside age, comorbidity, and immunological status when thinking about infection risk, particularly severe outcomes. And perhaps most importantly for students, this paper is a strong example of how careful study design, transparent reporting, and measured interpretation can support meaningful but appropriately bounded conclusions. Good papers don't just summarize what they found, they show us how to think clearly about what the findings can and can't mean. To summarize, this paper shows a consistent and graded association between obesity and the risk of severe infectious disease across large cohorts and multiple infection types. Its real strength lies not just in the size of the data, but in the clarity of the study design, the baseline characteristics, and the care taken in interpreting what the results can and cannot tell us. If you're learning how to read clinical research, focus less on the individual effect sizes and more on how authors frame their question, define their population, and acknowledge limitations. If you found this walkthrough helpful, you can find more videos like this in our further reading series, where the goal is to build confidence in reading and interpreting medical and biomedical literature. Thanks for watching. See you next time.